All right, welcome back, everybody. Hey, shout out to Mr. D-Lab's class watching this video. If anybody's in there watching this video. He didn't record today, so he asked me to send him this video. So shout out. The code word is
Apple.
Apple. The code word is Apple. Chance, the code word is Apple.
Do you think he's watching that video?
I don't know. Hey, here, I got the guided notes here for today. This is section 9.6. Now, thinking back to what we did on the 9.1 to 9.4 test, we did a lot of graphing, right? Pretty much the entire first half of chapter 9 was all about graphing. That's all we did. Graph, then graph some more, and then figure out different things, different pieces of the puzzle in terms of the different pieces of the quadratic that we graph, like the axis of symmetry. What's the equation of the axis of symmetry?
Negative b divided by 2 times a.
Negative b over 2a, right? So we were able to figure out what the axis of symmetry was based on the equation. We were able to figure out what the vertex was based on the equation. How do you find the vertex once you find your axis of symmetry?
You plug it back in.
You plug it back in, right? So we are able to find the axis of symmetry. We are able to find the vertex given the equation. Have I been able to find the zeros given the equation? The answer to that question is no. We have not been able to find the zeros given the equation. We were able to find the zeros given a graph. Where do you look to find the zeros of a graph? The x-axis. You look at the x-axis. That's where the zeros are, where it crosses the x-axis. So we can find them given a graph, but we have not yet found the zeros given an equation. I'll tell you this. Pretty much the rest of this chapter is finding the zeros given an equation. Like 4 sections worth of finding zeros. And we're going to learn 4 different ways to take an equation and find the zeros of that equation. The first way is what we're going to study today. Section 9.6 is solving quadratic equations by factoring. The second is going to be solving by square roots. The third is going to be this thing called completing the square. It's kind of a weird technique. The fourth is going to be the quadratic formula. Okay? The quadratic formula is like a method that will work every time. It's kind of difficult to learn. It's kind of a lengthy formula, but it's really, honestly, it's not too bad. But that's one of the ones that's like, okay, you know it's going to work every time. Because let me ask you this. My title of today's lesson is Solving Quadratic Equations by Factoring. Is everything always factorable?
No.
No. There are certain cases where we wrote prime. There are certain cases where we wrote not factorable. So there are going to be times when they're not going to be able to solve by factoring. When those times happen, we've got to fall back on a different method. So today, again, section 9.6, solving by factoring. We're going to do a lot of review. Remember all of chapter 8? All of chapter 8 was factoring? Yeah, we're going to take a look at some factoring today. All right, but first, to do that, we need this thing called the zero product property. The zero product property. Now, the zero product property says that if the product of 2 quantities equals 0, at least one of those 2 quantities must have been 0. What does it mean when I say product? What's the operation? Multiplication, right? When I have 2 things that are multiplied together, if one of those 2 things was 0, obviously the result must be 0. Here's what I mean. Say I had 2 things multiplied together. For this equation to be true, I could put a 0 here. And does it matter anything that I put there? No, doesn't matter at all. I could put a 5 there, a 10 there, a -3 there. I could put a 1/2 there. I could put any number I wanted to, and this would end up being 0. Would it change anything if I moved it over there? The same thing would be true, right? No matter what I get in the other blank, the solution ends up being 0. So if you've got two quantities that you're multiplying together, you can say that either of them could be 0 to make this equation true. Let me show you what I mean here. Let's take it our first example. Do you see how I already have like a factored form here? Like this looks like a trinomial that's been factored. Right? Something has happened to it already to be factored. Do you see how I have a product of two things? I have a product of two binomials here. What I can say is that either one of these, here are my two blanks now. Either one of these, because this equals 0, and only when it equals 0, because this equals 0, either one of my two blanks could be equal to 0. Okay, either one of them could be equal to 0. Thanks for that. Everybody, Dane Jarvis. Thanks for coming, Dane. Yep. Hold on, let me get you the guys' notes. There you go. You know, I am please. All right, so I just got done saying that either one of these two blanks could turn out to be 0, and this would be true, right? Like if just to reinforce it one more time. What if that underneath that turned to 0? Would it matter what's going on over here? No, because it would be 0 times whatever this ends up being equals 0. Is that same thing true when I shift it over here? Whatever I put here, as long as this turns out to be 0, whatever happens in the beginning one, doesn't matter. It's something times 0 ends up being 0. So what I can really say is that this could end up being 0, or this could end up being 0. This piece could equal 0, or that piece could equal 0. So what's going to happen is usually we're going to create for ourselves two little mini equations to solve. And then at this point, we just solve those little mini equations. We add 7 to both sides, so we get x is equal to 7. We subtract 2 to both sides, we get x is equal to -2. Yeah, we get 2 solutions for these equations most of the time. I don't want to say all the time. But in this case, I do have 2 solutions to this equation. I've got x equals 7, and I've got x equals -2. Now, it should make sense that we've got 2 solutions. When I talk about zeros of the function, zeros of the graph, you're talking about x-intercept, right? A normal standard quadratic, how many times does it have, how many zeros do you see? 2. There are 3 different options that you could have. You could have 2 zeros, 1 0, or none at all. See, this is the option in equation form where I have 2 zeros. 2 different zeros. Okay, let's try that one more time. Well, what happens if one of them is not a binomial and it's just a monomial? And I got x minus 2 and then just an x. Got x minus 2 and just an x. Okay, that's the exact same thing then. You set x minus 2 equal to 0, and you set x equal to 0. It's just easier because now one of them, you don't have any solving that you need to do. You just got x equals 0 over there. This one you do need to solve, x plus 2 plus 2. X equals +2. X equals 0. Another one with 2 solutions. And what are we finding here? We're finding the locations where this will cross the x-axis. See, that's what we're doing here. We're algebraically finding where these will cross the x-axis, where the zeros of the equation, where the x-intercepts are. All right, so what about if they have a little bit more difficult pieces there, like 3x minus 4, like 2x plus 5? The same rule still applies. The only different thing here is that when we create our 2 equations, it's just instead of a simple 1-step equation, it's a 2-step equation. You still do the exact same thing. You just solve, you set each piece equal to 0, and then you solve. We add the 4 to both sides. We get 3x is equal to 4. We divide by 3, 1.3 or 4/3. We subtract the 5. We divide by 2, negative 2.5. Again, these are the locations where this will cross the x-axis. These are the zeros of the function. Now, here's where the difficulty is going to come. These were pre-factored for us, right? So we understand what happens once it's factored. The difficulty is going to be getting it to this point here, okay? So let's take a look. If a quadratic equation is written in standard form, and again, it's got to be in standard form where this is equal to 0, then to solve the equation, we may need to factor before using that zero product property. Here's what I mean. You got to remember the flow chart. You got to remember what to do, how to factor. Solve the quadratic equation by factoring. What's the first step? What should I always do first? Good. Check to see if it's standard form and set equal to 0. That's done, right? In standard form, ax squared plus bx plus c. Is there a GCF? No, not in this one. It's always good to, okay, standard form, done. Is there a GCF? No. So now I say, okay, moving down the list. How many terms do you see? 3 terms. Is this an easy type or hard type of a 3-term? Easy type. Again, you tell the difference because is there a number out front here? No, then this is an easy type. Okay, so now what do? I find the factors of your last number that will add together to get middle. Remember the factors of 8, and I'm going to add together to get negative 6. Now, because it's a negative 6, what does that tell me about my 2 factors? They're both negative. They're both negative. So I could say negative 1 times negative 8, not going to work. Negative 2 times negative 4, bingo. There it is. Negative 2 plus negative 4 ends up getting us negative 6. So now I can factor it into x minus 2, x minus 4 equals 0. And now this brings us back to the exact same type of problems that we've had above. We set each piece equal to 0. We add 2. We add 4. What is that telling me? That's telling me that if I plug in 2 or 4 back into the equation, I should get 0. If I plug in 2 or 4 back into the equation, I should get 0. And you can check your answer to do so if you'd like to. Let's plug in 2. 2 squared minus 6 times 2 plus 8. Do I get 0? Hope so. 4 squared minus 6 times 4 plus 8. Do I get 0? Yep. These are the zeros of the function. This is where it crosses the x-axis. See, I can tell a lot about this function right now. What does the a being positive mean? Opens up. What's this 8 telling me? The y-intercept is 8. Could I figure out, if I wanted to go through the process, could I figure out what the axis of symmetry is? Yeah. Could I figure out what then would be the vertex? Yeah. I can now add on to that, and I can find my zeros as well, my x-intercept as well. Okay, take a look at the next one. What do I need to do first here? What's the operation? Somebody raise your hand and tell me, what's the first thing that I need to do? Right, how do I do that? Okay, Vader, subtract the 21. Get the 21 over to the other side, because I got to get everything on one side. Subtract the 21 over to the left side. So that's going to get me an x squared plus 4x minus 21 equals 0. Okay, you guys take it from there. Factor it and set each equal to 0. What two factors work here? Okay.
3 negative 7.
3 and negative, whoa, the other way around.
Oh, negative 3 and 7.
Good. Negative 3, positive 7. X minus 3, x plus 7. Now, you may be thinking about this. Did you just tell me your answers? Because they turn out to be the opposites. Because once I said x minus 3 equal to 0 and x plus 7 equals 0, because this was an easy type, once I add the 3 over to the other side, I get x is equal to 3. And then I subtract the 7. When you have an easy type problem, they end up being the opposites of the factors that you chose. Questions about that? Okay, let's take a look at this one. Now, do all quadratics have two x-intercepts? No. We just got done saying that sometimes quadratics only have one x-intercept. Let me show you that case. What are the factors of 9 that add to get to negative 6? Negative 3, negative 3. All right, so that means this will factor into x minus 3, x minus 3. I guess I should have gone through my checklist. Standard form, done. GCF, none. Easy type. Factors of 9 that add to get to negative 6 are negative 3, negative 3. So that means, I mean, I could do two separate equations, but aren't they going to end up being the same thing? X minus 3 equals 0. Add the 3. X equals 3. So this is a case where there's only one x-intercept. What does that look like graphically? Well, that just means that the x-intercept, that 3, is actually its vertex here. Kind of looking like that. If I wanted to get a little bit more specific, I could plot some points, but I know that it's going to be y-intercept of 9. I do know that. But this is the case where it only has 1, 0. All right. So, life is not always unicorns and rainbows. Sometimes we don't have just easy type factoring problems. This is a hard type factoring problem. So let's dust off the cobwebs a little bit. Let's remind ourselves how to factor. I gave you an easy hard type. Okay. So first off, is it in standard form? Good. Is there any GCF? No. Okay, so we're stuck. This is a hard type factoring problem. So we got 3 times 1. Remember, you take first number times last number. 3 times 1 is just 3. And then I find the factors of 3 that add together to get to negative 4. What are they? Negative 1, negative 3. Negative 1, negative 3. Negative 3, negative 1, negative 1. It doesn't matter the order. And now we leave our first term and last term the same. 3x squared and the plus 1 sitting out on the end. That stays the same. What changes is this middle term. So we say minus 1x minus 3x. And now we factor by grouping. What's my GCF of my first 2 terms? Just an x, right? A 1x if you wanted to. So we divide it out, we factor it out, leaving a 3x minus 1. Now, what do I pull out of my second set?
Negative 1.
Negative 1. It leads with a negative. Be careful. So negative 1. We divide out the negative 1 and we get a positive 3x minus 1, right? Negative divided by negative with the 3 got us a positive 3x. Positive 1 divided by negative 1 got us a negative 1. So that means, look, the goal was, again, to get my parentheses to look exactly the same. Goal achieved. And now I say 3x minus 1. And then the other piece is everything that's sitting on the outside, x minus 1. And it's still all equal to 0. I kind of leave that behind a little bit, but you should always remember that it's still all equal to 0. Because in the end, I'm not looking just to factor, I'm looking to solve. So I say 3x minus 1 equals 0, and then an x minus 1 equals 0. The end process is the same. You still set them equal to 0. See, remember all that thing, all those trinomials we factored in chapter 8, all those 3 terms that we factored in chapter 8? What we're going to do now is take it a step further and set each of those factors equal to 0. And solve that little mini equation that we're given. We have a 3x is equal to 1, and we divide by 3, we get x is equal to 1/3. Or if you wanted to write it in decimal form, 0.3 repeating. And then we add the 1 over to the other side, so x is equal to 1. So here are my 2 solutions. You're going to notice when you get a hard type factoring problem, your zeros come out to be decimals. When it's an easy type, they're going to be whole numbers. Can we try another one? Yeah. Nah. Let's try this next one. What's the easiest way to get this into standard form? Do we all agree that this is not in standard form? Right. Eddie, what's the easiest way? Yeah. Could I have subtracted the 20x and subtracted the 50? Sure, but it's easier if you just make it positive. I add the 2x squared over to the other side. So now this is going to be 0 is equal to, does it matter where the 0 goes? Nope. Could go on the left side, could go on the right side, doesn't matter. So we got 0 is equal to 2x squared plus 20x plus 50. What do I do next? What is the GCF? Yeah, there's a GCF of 2. Be careful there. You're going to want to pull out the GCF because it looks like a hard type problem. But then when we factor out the GCF of 2, that's going to give me an x squared plus 10x plus 25. And hey, look at that. Now it's an easy type. Yeah, that. Factors of 25 that add to get to 10. What are they? 5 and 5. Now, leave the 2 out front. So I've got x plus 5, x plus 5. Now, do I need to do 2 separate equations with this? No. I could just use one copy of that x plus 5 equaling 0. We subtract the 5. We get x is equal to negative 5. And that's my solution. Now, do I have to do anything with that 2 that got brought out front? Now, if I truly, I hope, please don't say x equals 2. That's not true. It's not x equals 2. Is there even an x out there with that 2? Because the rule was, I set the products, all the pieces of the products equaling to 0. So really what I would do, since that is a whole chunk equaling to 0, I would really set it as 2 is equal to 0. Are there any solutions there? Like, that's a contradiction. Are there any solutions? No, there's no solutions with that little piece. So here's the moral of the story. If you have a GCF that is just a number, it does not play a role in your factors. If you have a GCF that is just a number, it does not play a part in your factors. It just kind of goes away. It does not play any role in your zeros. Okay? It does other things, like it affects the axis of symmetry. It affects the vertex. It affects all the other points, but it does not affect the zeros of the function. Okay? So we only have x is equal to negative 5. There is no solution here. Let's try one more. Now, this is a case where I would take the time to move everything to the left. You want to know why, rather than moving the 30x over to the right? Why would I want to move everything over to the left side instead? Because they're both negative. And I'm going to end up adding both of those things over to the other side to make everything positive. And then you know me, I'm a positive guy. I like to stay positive. I'm a positive guy.
Yeah.
You don't think I'm a positive guy? I feel like I'm a pretty positive dude. Thanks, Gabby. Gabby's got my back. Thanks, Gabby. I add 9x squared over to the other side. So next step is going to give me a 9x squared plus 30x is equal to negative 25. And now I add the 25 over to the other side. So yeah, I mean, I guess I could have subtracted the 30x over. But again, I like it better as positive. Because if I left it as a negative, I would have to factor out all of those negatives. All right. So is there a GCF? I mean, I could divide 9 by 3, and I can divide 30 by 3. Can I divide 25 by 3? Bummer. All right, well, that must mean this is a hard type problem. What's 9 times 25? 225, you mean?
Yeah.
Jake.
Why did you add the up to like 9x squared and not the like the last problem you did using that squared?
Say what?
Like I don't know how to explain it enough. Anyway, you added 9x to this. Why did you add the 2 there? Why?
Why did I add a 2?
Why didn't you add the 2 for this one?
I did. I did. Yeah, look up here. You big. You big. All right, let's jump back. Sidetrack there. Anybody find him yet? 15 and 15. 15 and 15. This is actually one of those special cases where is 9 a perfect square? Yeah. Is 25 a perfect square? Yeah, so maybe 225 is a perfect square. Let's take the square root of 225. Bingo. 15 and 15. So we say 9x squared plus 15x plus 15x plus 25. And now we factor by grouping. We pull out our first 2 terms, we get a 3x from our first 2 terms. Leaving us with a 3x plus 5. We do the same for the second 2 terms. We're going to pull out a 5. Leaving us with a 3x plus 5. So my solution is, or not yet, my factored form is 3x plus 5, 3x plus 5. This is another one of those where I've got the same thing as my factors. Do I need to write them both? No, let's just write one of them. We set one of them equal to 0. I'll pick the first one. We subtract the 5. We divide by 3. Sorry for my poor handwriting. Negative 5/3, or as a decimal, negative 1.6 repeating. Again, fraction, decimal, doesn't really matter. Know that that's not 2 solutions, that's just one. Okay. Last problem is a word problem. Okay, we got this diver. He's on the top of a diving board. He's going to go. All right, so let me draw out a picture. Here's my dude. He's a diver. Currently got 2 tan. It's all red. So funny. He's going to jump off and he's going to land in the water. Forgot to draw like a ladder up here. Now, he's going to jump off and then look at his path. what does that look like? Looks like a parabola, doesn't it? Doesn't it look like a downward facing parabola? Like if I extended out the whole thing, wouldn't I see the entire parabola? I see an entire downward facing parabola. Does it make sense that it's downward facing? Look at the equation. The a value is negative. All right, so negative 16t squared plus 8t plus 8 is our function. Now, what is this point? It's the 0. It's the 0. Right? That's a 0. Graphically, that's a 0 of the function. So what I'm actually going to find here is where this equals 0. So you know how in word problems we were just finding like the maximum value? We're not just stuck to finding the maximum anymore. We can actually find a 0 within a problem if we'd like to. So we factor that down. It has a GCF. The GCF is -8. We divide out a -8 to each piece. And that will get us a positive 2t squared, a minus t, and a -1. Now, let me ask you, does that -8 play a role in our zeros? No, it's just a number. I didn't pull out a GCF with the letter, so I just kind of ignore it at this point. So I factor this here. 2 times -1 is a -2. Factors of -2 that add to get to -1 are -2 times 1. I keep my first term, I keep my last term, and I rewrite my middle. Let me erase away some water. And now we factor by grouping here. We pull out a 2t. We're left at the t minus 1. There's no GCF, so we pull out a 1, and we're left with a t minus 1. So my two factors are t minus 1 and 2t plus 1. Still all equal to 0. And now we set both pieces equal to 0. We say t minus 1 equals 0, and we say 2t plus 1 equals 0. Now, I add the 1. I get t is equal to 1. Subtract the 1. I divide by 2. I get -1/2. Now, could I actually hit the water at 2 different times? No, that doesn't make sense. So what's wrong with one of these? What's that? It's negative. I mean, you can have a bad time, but can you have a negative time? Isn't that funny? I make that joke all the time. You can have a bad time, but can you have a negative time? I hope Mr. D laughs. Students laugh at that. No, that cannot happen. You cannot have a negative value for time. We're not time travelers here. So t is equal to 1. So we say 1 second. That's how long until he hits the water. Questions about that? All right. Homework is going to be up here on the board. Let me stop the video. So long, everybody. Playing along at home.